This video is on complex number arithmetic. First, we need to define a complex number. So the set of complex numbers is all of the numbers that can be written in the form a plus bi, where a and b are real numbers, and of course I is the imaginary unit. And that imaginary unit is equal to the square root of -1. So some examples of complex numbers: 5 plus 3i, 1/2 minus 8i. Your b can be negative, your a can be a fraction. Your a can be 0, -2i. You could write that as 0 minus 2i, or 0 plus -2i, to make it fit into this a plus bi form. 15, because this can be written as 15 plus 0i, which makes it fit this form. Pi plus I root 2. Pi is a real number. The square root of 2 is a real number. When we have a radical like this, we write the I in front of it. That way there's no confusion, no ambiguity as to whether or not this radical bar extends over if it's in front. So those are some examples of complex numbers. Every complex number has a real part and an imaginary part. So your real part is the part that's not multiplied by I. That real part might be 0, but technically there's still a value there. There's still a 0 value for this particular one. And every number has an imaginary part. That imaginary part, again, might be 0, but you could talk about the imaginary part of this number if you needed to. So when adding and subtracting the complex numbers, if you're subtracting, distribute the negative and then just combine like parts. Combine your real parts with your real parts and your imaginary parts with your imaginary parts, just as if you're combining like terms. So for example, if we have 100 plus 3i plus 2 plus 50i, we add our real parts together and our imaginary parts together. Our real parts, 102, gives us the 102, and 3 plus 50 gives us the 53i. When we're subtracting, we need to make sure to distribute that negative across that parentheses, and then do the same thing. We combine like parts. So we get 97 plus 9i for this particular one. So when multiplying complex numbers, you need to distribute and multiply as two binomials. Some people like to talk about FOIL at this point. But the important thing is to multiply everything by everything. And when you simplify, remember that I squared is equal to -1. So it's clearest with an example. When we multiply these, the 2 times the 5 gives us 10. 2 times 7i gives us the 14i. 3i times 5 gives us the 15i. And 3i times 7i gives us 21i squared. We can combine our like terms to get the 21i, and then remember I squared is equal to -1. So 21 times -1 is -21, and then when we combine our like terms finally, we get -11 plus 21i. Now we're going to talk about conjugates. The conjugate of a complex number a plus bi is the number a minus bi. Notice how the real part stays the same and the imaginary part changes sign. Let's have some examples. So if I'm going to start with 2 plus 3i, my real part is going to stay the same. The 2 will stay exactly like it is. And my imaginary part will change sign. So that gives me 2 minus 3i. Next, if we start with 7 minus 8i, my real part will stay the same. The 7 will be exactly like it is. And now my b is negative 8. So negative b is the negative of negative 8, which is positive 8. So I end up with 7 plus 8i. Notice how the sign of the imaginary part changes to whatever the opposite is, and the real part always stays the same. Now, conjugates have some interesting properties when you multiply them together. So, if we multiply this out, 2 times 2 is 4, 2 times negative 3i is negative 6i, 3i times 2 is 6i, and 3i times negative 3i is negative 9i squared. Notice how my negative 6i and my positive 6i are going to cancel out. And then I'll be left with my 4 and my negative 9i squared. But I squared is negative 1, so negative 9 times negative 1 is a positive 9. So really, I'm left with 4 plus 9, which is 13. And our next example, when we multiply 7 minus 8i times 7 plus 8i, 7 times 7 is 49, 7 times 8i is 56i, negative 8i times 7 is negative 56i, and negative 8i times positive 8i is negative 64i squared. So notice again, 56i and negative 56i, our two imaginary parts, are going to cancel out. I have an I squared here. I squared is negative 1, so negative 64 times a negative 1 will be a positive 64. And 49 plus 64 is 113. Now, let's do this in the abstract. If I have a plus bi and I multiply that by a minus bi, a times a is a squared, a times negative bi is negative abi, bi times a is abi, and bi times negative bi is negative b squared I squared. So here my minus abi and plus abi, those will cancel out. I squared is negative 1, so b squared, negative b squared times negative 1 is going to be positive b squared, and I'm left with a squared plus b squared. And remember that a and b are both real numbers. So whenever you multiply a complex number by its conjugate, you always get a real number. This is a very useful thing when we're doing division. So we will use the conjugate of the divisor in order to divide complex numbers. Let me show you what I mean. So here we have a division of complex numbers. I want to perform this division and get a single complex number in standard form. I need to get this out of the denominator. So I'm going to multiply by 2 plus I over 2 plus I. I'm allowed to do this because this is just a fancy form of 1. It's a number over itself. So if this is equal to 1, it does not change the value of my fraction. But I do know that when I do this, my new denominator that I get from multiplying these two denominators together will be a real number. There won't be imaginary numbers in the denominator anymore. So let's look at this. When I multiply my numerators together, I'll expand to that in a moment. When I multiply my denominators together, I will get a squared plus b squared, which in this case is 2 squared plus 1 squared. So my new denominator is 5. When I multiply out my top here, 2 times 2 is 4, 2 times I is 2i, negative 11i times 2 is negative 22i, and negative 11i times I is negative 11i squared. I can combine like terms, remembering of course that I squared is negative 1, so this goes into this 15. 4 plus 11 is 15. And then I have 15 minus 20i over 5. 5 is a factor of the entire top. I can factor out that 5 and then cancel it. And so what I'm really left with is 3 minus 4i. Now, sometimes you will have fractions left. This was a particularly nice problem because 5 was a factor of the entire top. But you'll always have all your real numbers out of the denominator and be able to express it as a single complex number. Finally, I want to talk a little more about simplifying powers of I. You have already done the imaginary numbers learning activity, and you've noticed from that pattern, I hope, that if n is a multiple of 4, then I to the n is equal to 1. You got 1 for I to the 4, and I to the 8, and I to the 12. And that pattern repeats over and over again. We can use this to simplify I to the other numbers. So I to the 162. 162 is not a multiple of 4, but 160 is a multiple of 4. So I can break this apart and write I to the 162 as I to the 160 times I squared. When I do the reason that it is useful to do this is now I know that this entire expression, I to the 160, this is just a fancy form of 1 because 160 is a multiple of 4. That means that this is equal to 1 times I squared, and I squared is just negative 1. If you've got negative exponents, it can be more useful to multiply in by an I to the n. Let me show you what I mean. So if I have I to the negative 401, I want to multiply by a multiple of 4 that's just bigger than 401. When I do this, I can add these exponents together. No, first, notice that I'm allowed to do this because this is a fancy form of 1. I'm multiplying by 1, so I haven't changed to the value. I can add these exponents together now, and negative 401 plus 404 is 3. And I cubed, we know from that handout, is equal to negative I. So the only values that you have to memorize are the first 4. And then just remember that when n is a multiple of 4, I to the n is 1. And that concludes our video on complex number arithmetic.